So today we want to look at the last piece we need to actually hook our Otter up to actual hardware, right? So we have this device that executes code, and so how do we connect it to kind of stuff we can touch and feel and input and output? And so if we kind of look at what we have, right? Everything that we've done up through, essentially hardware 6 has been to create this. My colors right. Where this is our, I've been calling it my CPU. I think the other thing calls it MCU, right? Kind of use this a little bit interchangeably, but this entire architecture diagram, this whole thing, right, goes in one box, right, where we have these inputs and outputs, right? So right, we have our reset, this INTR thing that we haven't talked about. We have a clock. Then we have this IO bus in. We had in IO bus address. IO bus out. And IO bus WR. So maybe we'll deal with the easy thing first. Reset. What do you think we're going to hook up to reset?
A button?
Yeah. And so I'm going to hook up button C, right, which is the center button. So that's the one, right, that I would probably use. And so that one's pretty easy. So if we look at other inputs, right, we could hook up multiple things. And so one thing that we know that we use is we use switches, right? I've mentioned previously that we can look at an option to add a keyboard, right? Maybe we want to use the other buttons as an input, right? All of that stuff has to go where? Where does it have to get to in our CPU? Where does that data have to come in at?
IO bus in.
Yeah, it has to come into IO bus in, right? And this should sort of make sense because, right, I would access those things using what type of instruction? How do I read from switches or read from some external buttons or?
Load.
Yeah, a load. And a load always grabs its data from where?
The memory segment.
Yeah, specifically it grabs it from this DOut2, right? So somehow the data has to come from something external and get routed somehow to DOut2, right? And so this memory unit must do some of that, but ultimately it has to come in IO bus in, right? That's where this data has to come in somehow, right? So the question is if I have multiple things that I'm going to send into IO bus in, how do I connect all of them? I've only got 32 bits. I can't connect everything.
Can you use a mux?
Exactly. It's exactly what I do. So I set a mux. And so this is how I can have multiple things get routed into IO bus in, right? Depending upon what I want to select. So how do I select which of these things in my mux?
The address given to the memory.
Okay, so how does this mux get access to that?
Guess it would be directed to it, right? From, is it mem address 2 or 1?
IO bus address.
Right, right. So if we look at where this address 2 is, right, this is the same signal that is IO bus address. Right. So this is the same address, the same value that's going into ADDR2. And so that's why this is an output here, because it's going to be the selection for this mux, right? Move this down. This look better. Okay. And so by picking a certain address, right, that chooses a certain option on my mux, which then routes that into IO bus in, right? And so if I want to read from switches, right, I'm going to give it an address of 11.0.0.0.0.0, right? And so that in my mux has to be an option where I'm going to choose which one of these gets put to where. This mux is ultimately where I pick what goes where in my memory mapped IO. Right, so this is where I would give switches that specific address, and maybe my keyboard or my buttons some different address. Questions on that? This INTR, right, we're not going to deal with it for now, right? We don't have it connected to anything, so we can leave that alone, or we could hook it up to zeros, you know, which is fine. You don't have it connected to anything inside yet anyway, but so we don't need to worry about that. So the other thing that we can look at is, you know, we want to output to different stuff, right? And so we could maybe output to our LEDs. We could output to our 7seg, right? There's other things that we'll look at outputting to. Like we could output to a VGA monitor, but for now, we'll just leave it these two. So where's that data come out? Like, where's the data that I send to the LEDs or the data that sends to the 7seg? Does that data come from?
IO bus out.
It's IO bus out. Okay, so how do I route it to, and how do I connect it to LEDs and 7seg?
Use a demux with the address as the control bit.
Okay, yeah, so we could use a demux. All right. Put this down just a little bit. Kind of reversing the same process. Questions on that? So this is pretty good, but not quite right. We still have a problem with this setup. We know what our problem is.
Is it constantly going to be writing?
Yeah. There's constantly data on IO bus out. There's always data on this address. And worse, what happens if I'm not selecting the address for LEDs? What's this demux going to output?
Zeros.
Zeros probably seems likely, which means my LEDs are only going to come on for the flash of executing that store. And then they're going to go off, right? So how do we fix it?
Registers
Yeah. Where?
after the mux, but before the LEDs and 7sig.
Yeah, the problem is we need to save this, right? So we need to add some registers. Okay, so where this is essentially D and Q. Okay. Now, did that entirely fix our problem?
No, we need to connect the, well, wait, never mind. I'm not sure.
When does a register update its value?
If an enable's on,
Do I have an enable on these registers?
IO bus right.
Exactly, right? So right now, as these registers stand, right, they would update on every rising edge of clock, which means I've really only bought me a clock cycle, which isn't going to be that good. So that's what I need to do is I can add an enable to these. So that I only turn this on when I want to. And so that's why I have this IO bus WR, is because it's only going to tell these registers to come on when I'm actually writing to them. And so that's why IOWR only comes on when I'm writing, when I'm doing a store instruction to a memory mapped IO address, right?
So won't there still be a problem though? Because when you enable that and you send a signal into the demux, it's going to send zeros to one and then the proper value to the other, right?
So technically, yes, this sort of has all the right hardware, but it's actually not wired properly, right? Because as you said, when I send the enable, I'm actually enabling all the registers at once. Any idea how I fix this?
Could you set the enable before the mux in a way so that it only writes to, sorry, I actually don't know.
Could you use another demux
For what?
for the enable? So
Do-
it
if I
would
have-
be connected to the same control as it'd be connected to IO bus address as well.
Right. Question is if I do that, do I need a demux for data?
No, you wouldn't.
Yeah. So this probably doesn't seem to make as much sense, maybe initially, but it is maybe a better representation of what happens. Right. So the data goes everywhere, but it only gets saved whenever I'm actually writing to that specific address. This will be closer to what the hardware is that we actually build. And by we, I mean me. I'm giving you the file. Questions on that?
Wait, you said you're giving us the file for the wrapper?
Mhm.
Ah,
Like, why am I paying attention to this?
no, that always because I started writing it already.
So yes, this entire thing is, and actually we've got still one other slight problem. But this entire thing is what's in the Otter wrapper. And so it's on canvas. Now, a couple other things to maybe make this a little better. This 7seg, right? When we write to the 7seg, if you want to display 10 on it, we've been just writing 10. But 10 in binary is not actually going to turn 10 on the 7seg, right? You should remember that from 133. So what do I need to actually put in here?
A 7-segment decoder.
Yeah, so this line should actually get pushed back. So actually, I have a, so I'm redrawing this. Kind of run out of room on my paper here, but my LEDs are actually here. And this is my 7seg. Sorry, it's probably not very readable. We'll just write it here. So this is my 7seg decoder, where this is actually writing to probably, right, if you recall from 133, right, you had your cathodes and your anodes, right, and it had some clock, right? So I give you this too. I'm assuming that you wrote one in 133. If you didn't, shame on you, and you should write one, because it's a fun project to do. You'll be a better person if you have. I'm only half joking. Right, so I give you one of those that you can use. You just have to, make sure you know how to wire these cathodes and anodes up properly. But you can read the code, so it should be in there. And so if I wanted to add other stuff, right, I could have, a VGA driver, right? There'd be some sort of thing here that would be a decoder for my keyboard, right? I'd have some sort of keyboard driver, right, that would give me my 32-bit data off of it, right? And so I can add stuff. And so, it's kind of interesting in that when we move past 233 and we look at, right, using one of these types of microcontrollers, right? Like when you get to 329 and we use this part that we spent pretty much our entire time on is the boring part that we don't look at all, right? In 329, we don't care about this. This is dull and boring and everyone does it, right? The interesting stuff is actually all of this stuff. And so in 329, we spend pretty much all of our time looking at all of this interesting stuff here. And this part, right, unimportant. CPUs are a dime a dozen, right? So anyway, as you move towards, right, making this thing usable, right, a lot of differentiation in products. When you look at what makes an Arduino or an Atmel chip different than a PIC, than STM32, than a TI, whatever, right? It's usually actually all of this other stuff on the inputs and outputs that make it interesting. This part in the middle, kind of boring. Cool. Questions on that? So there's one other aspect to this wrapper, and it involves the clock. So coming off of the basis 3 has a clock. And what is the speed of the clock on our basis board? Right? It's got this external oscillator. I think it's back here on the back, I think, actually. I think that's it. It runs at what speed? You remember?
100 megahertz.
100 megahertz. Okay. So if we maybe do some quick math, 100 megahertz gives me a clock period of what?
10 nanoseconds.
10 nanoseconds. Now, if you recall from one of the software assignments, I said that the Otter would execute instructions in what type of time period? Remember?
40?
It was 40 nanoseconds. Now, how many clock cycles does it take to execute an instruction on our CPU?
Typically 2.
Typically 2, right? Unless it's a load, it's 2. So that means if I'm running at 100 megahertz, it should take how long?
20 nanoseconds.
I said it's going to take 40, which means what?
We're going to be using a clock divider to bring it down to 50 megahertz.
Yes. So there is this divide by 2. Right. So that we have this clock divider. Any idea why we put this clock divider in here? I mean, if 50 megahertz is good, 100 megahertz has to be twice as good.
Well, is it because our basis board can't conduct the signals fast enough throughout the entire CPU?
Basis board's fine.
Is it our design is not fast enough?
Might not be, right? So yes, this is the issue, right? And so if we think about, what needs to happen in one clock cycle, right? So let's think about this, right? At the beginning of the execute cycle, right, we get a rising edge. Rising edge puts out a brand new machine code, right? That machine code comes out and has to go to the reg file. The reg file has to then output the data on those regs, or it has to go through the immediate generator and output the data on that. That data has to then get routed through these 2 muxes, which need to be selected right because the decoder right? So the coder has to take the machine code in and then select the proper one for the selects for these muxes. And then the data's got to go through them. It's got to go through the ALU. It's got to come back, right? Maybe it has to go through this mux and get put into this WD with a certain amount of time before the next rising edge, right? So that we meet that setup time that you probably talked about in 133. And so all of that needs to happen. And so depending upon how well you design some of this stuff, depends upon what kind of propagation delay you have. Now, obviously, one of the big things here is the ALU. And so looking at your ALUs, they all seem relatively good, right? I don't see any really poorly designed ALUs. But then the other thing that's sort of an unknown is this decoder, right? And so if this decoder is slow, then these ALU source selects change late, which then means everything that happens after them is happening later, right? And so that could be a problem. And so what you find is that everything that we've been dealing with, right, like all of the debugging that you've been doing, you've been trying to find logical problems, right? There's some problem in your logic, right? You're not doing the right thing with the right set of inputs. Those are actually the easy problems to solve. The hard problems to solve is timing. And so we're not going to make that be a problem. And so we're just going to slow everything down so that you have plenty of time. And so that's why we put the divide by 2, right? So that maybe your decoder isn't as well designed as it could be. We add extra slack time in so that it still works, right? So that's why we put this in. Questions on that?
What sort of things would make like our decoders slower to the point where we would need a clock divider? Like I don't know what specific things in the program.
So some of it goes back to maybe that we talked, right? I said that your ALU should have all of your things happen in parallel as much as possible with one big mux, right? So when you think about longest path, right, you want to go through the least amount of stuff. And so you want as much in parallel as possible. So if you kind of apply the same thing to this decoder, right? Some of you have, if you look at your elaborate designs, you see long chains of muxes. Right? So if you have a long chain of muxes, then your path has to go through each one of them. And each one of them adds a little bit of delay.
So it'd be things like
if we had
like too many like case statements or if statements and stuff like that.
Possibly,
those would
right?
More like, yeah.
Right. And so sometimes it's not whether it's too many, it's it might be how, right? So
like if one feeds into the other.
Right. So this goes back to right, case statements tend to make big muxes. If else's tend to make chains of small muxes. And so how you coded that could create slightly different logic as far as how the synthesizer then makes the hardware that you described, right? So you described the same logic, but you describe slightly different hardware, which is kind of, this sort of nebulous thing to wrap your mind around, right? That at the end of the day, everything you're doing in Vivado is you're telling the synthesizer how to build hardware, which is maybe an odd thing to think about. But so depending upon how you've done it, right? You could be creating, you could be creating your design with, longer chains of stuff as opposed to more stuff in parallel. So we like big muxes. We don't like chains of small muxes. And so that is the advantage of our FPGA, is that we can do lots and lots and lots of stuff in parallel. And so the more we do in parallel, the faster it is. And so we try to purposely do that as much as possible. That's also kind of leads to why we split these two things up, right? These all could have been one unit, but we split them up. If you ever take 333, right, for the CPEs, and you want to take 333, you take this adder and you make it better, and you'll see another reason why we split these up, right? As far as to make this better, that sort of has to happen. So there's reasons where that come in to play. So anyway, so depending upon how you've done things, that's sort of the big path. The path that I trace is typically the longest path that we have to worry about, that we need to make sure that happens. And so to just kind of avoid any sort of timing issue, we just go slow. And really, 50 megahertz is pretty freaking fast anyway, right? Like, I mean, it's not like that's that slow. In terms of microprocessors, in 329, the fastest we get this guy going is 48 megahertz. And so, we've got our CPU that has an effective speed of 25, right? If it's doing an execution every 2 clock cycles, right? It's got an effective speed of 25. Just for a microcontroller, it's actually pretty fast. If you used an Arduino board, right, you got a whopping 8 megahertz, maybe 16. Woohoo, right? I mean, it's not that impressive. Right, we're going faster than that, way faster than that. So, my thing's cutting out. Is it better?
Just occasionally.
Okay.
You drop out for a second or two every little bit.
You get every third word. That should be enough. Questions? Okay. So then, since I give you this wrapper, right, I want to look at the code, right? And so, right, first thing we kind of see, we've got our inputs and our outputs here, right, which sort of makes sense, right? Our clock, this is our button that we're going to use for reset, switches, LEDs, cathodes, anodes, right? These will be all the things that you will then essentially add constraints for, right? So this file you should be able to just add it to your hardware 7, and it should then become the top module, right? So we now have a wrapper with the CPU inside it, with then all of the other stuff inside of it, right? So modules inside of modules inside of modules, right? It's almost like we're doing a real design here, right? And so your constraint file will be to map to all of this stuff, right? And that works exactly the same way it worked in 133, right? Which I'm assuming you know how to do a constraint file. If not, if you look at the tutorial on Canvas on how to do a system Verilog module, I take you through the end and I talk about constraints files there. And so you can kind of review it on that tutorial. But anyway, so connect your stuff up. And then if we keep looking at this code, the next thing I do is we have this local parameter. And so what this local parameter does in system Verilog is it's sort of like in C, if you had this pound define, or you create some sort of constant, right? Or maybe to put it in terms of our assembly code, right? When we have this .eqv and we have some text and we make it equate some number. And so we can kind of use this text as a substitute for the number. And so that's what we're doing. And it's a local parameter because it's local only to this system Verilog file. So these sort of constants only kind of exist inside this file, nowhere else. So it kind of keeps the scope limited. But so if I look at what I've done, what am I creating with these local parameters?
Output addresses.
Okay. So what do you mean by that? Output addresses for what?
These are the memory mapped IO addresses for the LEDs, 7seg, and switches.
Yeah, right. This is this hex value that we've been using for our switches, right? We would read from 11 L0s, and that was our switch address. And 110020 or 110040, right? That was our address that we would write to for our LEDs, or we'd write to for our 7seg. So these are just our memory mapped IO addresses, right? And so what we're doing is we're creating a sort of text label for it so that we don't have this, hard-coded magic number just show up somewhere, right? So we're making our code kind of easier to read, and we're kind of defining these addresses. So this is essentially the spot where in our wrapper that we are picking what stuff is connected where, right? And so I kind of hinted at that right in this mux, these muxes are where you actually specify all the addresses for all of your peripherals, right? This is where we get to pick it. So if you wanted the switches to be 11,250, you could pick it, right? If you wanted it to be 12,004, right? You could pick it. The only thing that's yeah.
Okay, so I'm just a little confused. When we actually take the auto wrapper file and just input it in Vivado, do we have to go in and like change the names in the code so that it actually connects to our CPU? Like change the names to the ones we used?
Yes, you will.
So just in
And we'll
that,
get
just in
there.
that part where you called the otter MCU in the code, we'd go in there and just change those to what ours are, and it should just work.
Yes, it should.
Okay.
So, going back, right? So we were talking about the memory mapped IO addresses, right? Since you're building this mux, you get to make this select go to whatever you want. Right? The only sort of stipulation is that the address you pick should be a multiple of 4. Why? In fact, it has to be a multiple of 4. Why?
Because it would have to be compatible with the save word instruction.
Yes, right. It has to be on a word boundary, right? This IO bus is 32 bits. And so to stay on that 32-bit word boundary, you would need to make sure your addresses are a multiple of 4, right? And that's just so that this stuff works internally correctly. But so you can pick whatever number you wanted for this. And so that's where your choice of where you want to connect stuff is largely up to you. The important thing is it has to match, right? So whatever address you give to switches here, needs to match whatever software that you're running inside. Because your software says load from this address, and it's going to load from that address. So hopefully your hardware matches, right? So that it actually does what you wanted it to do, right? So as long as the hardware matches the software, right, you're fine as far as picking an address for whatever. We've been using these addresses on all of our software assignments, so I'm just keeping them consistent. Right? But right, if I wanted to add more, right, I just need to give it a new address and list it in here. Right, that would be kind of my first step. Okay, but so that's what those local parameters are for. So then the next thing, right, notice I'm creating some signals, right? These are all the signals that I'm going to connect to this thing, right? So again, wrong. Right, notice I've got some wires, right, wires that are connecting between different stuff. And so I need signals to make those connections. And so here's where I connect my CPU. Right? And so this you may need to change, right? Because you may have called it something different. Your module is probably not called CPU. And you probably did not use these names for all of your stuff, right? So you need to match this, right? So that it knows how to connect stuff properly, right? But this is the same as connecting any other module that you've done, right? This isn't anything new, right? Notice this interrupt thing, this INTR, I'm connecting it to 0 for now because we're not using it. So I'm just connecting it to 0. I've got my 7 segment here. The only thing maybe odd about the 7 segment is it has this mode input, which may not necessarily be intuitive. You have the code, so you could read to see what the mode does, but I'm just hard coding it to 0. One thing that might be worth mentioning is, you notice how I've organized this code? I've kind of laid it out in nice organized blocks, little comments, right? I'm assuming you're all writing your code in this same organized, neat, easy to follow fashion, right? Okay. Next thing I'm doing here, right? This. What is this doing?
That's the clock divider. So every rising edge on the 100 megahertz clock, it switches the value of the 50 megahertz clock.
Yes, right. And so if we think about how that works, so if I have my 100 megahertz clock, and anytime I want to do anything with clock dividers, I always draw this out, right? Ask anyone that took me for 133, right? Anytime we did stuff with clock dividers, I'm always like, draw the thing out, because the numbers never make sense. Because they're always kind of the inverse of what you want. But so if we draw this out and look at what it's doing, right? So on the rising edge, right, it toggles. So it changes. And then it doesn't change again until it hits another rising edge. And then it doesn't change until it hits another rising edge. And then another rising edge. And so it's kind of easy to see that, right, one time period here is 2 clock cycles. Right? So the time period is twice as long, right? Which gives you half the frequency. And so right, that should sort of help you make sense of this is how this thing is dividing the clock by 2. Right? It's a relatively simplistic clock divider. So then we get to this always cone block. And so what is this thing doing? What kind of hardware, what am I describing here?
Is
Is
that
that your-
the
For your enabler?
My enabler?
The mux to enable when to enable the registers for your LEDs and your 7-sec?
Not here.
is that your mux
Yeah, which one?
going into the taking your switches slash buttons, wait, switches and keyboard and all that stuff?
Right, yeah, this is my input mux here. All right, now, right now, I've only got one thing hooked up to it. But so, right, it's a combinational block. And I'm looking at this address. And based upon my address, I'm assigning my IO bus in signal something. Right? So, yeah, this is setting this signal to something based upon what my address is. Right? And so if I wanted to add my keyboard to this, or I wanted to add, my other buttons or something else, how would I do that?
Do like buttons x address equal, and you would give is that a that's a constant or a parameter? Is you use that?
Mhm.
Okay, yeah. So you would define a new parameter for the buttons or whatever, and have a case statement for that.
Yeah. So if I wanted to add something else, some other input, buttons, a PMOD, whatever, right? I first define an address for it, right? That's step one. So I give it an address, make sure it's a multiple of 4. I had an address that wasn't already used, right? So a unique address, multiple 4. And then I essentially just add another line, right? Another line and route whatever that is to IO bus in. Here, what am I doing in this block?
Now I think that's what I was looking at earlier. It's the mux for your to determine when to enable for the register for your LEDs and your 7-sec.
Yeah. So I've got an always flip-flop. Notice it's checking on the 50 hertz clock, right? And that's because, right, if I think about this IO bus can't change faster than 50, right? Because nothing inside is changing faster. So I don't need to check these any quicker. So the 50 hertz works. So I'm essentially updating those registers. And so this whole thing sort of gets kind of all combined into one block, right? If I look at actually what I have here. And so the first thing I look for is what?
Make sure you're only writing when the enable is high.
Yeah. So if this signal isn't a 1, then I don't need to mess with any of these, right? They can all stay whatever they are. So I only need to think about changing these if this thing is a 1. So if this isn't a 1, leave everything alone. But if this thing is a 1, then I've got to update these registers, right? And so I update it by, again, kind of using this case statement off of my address. And so I take whatever the output of my bus is and I connect it to whatever I need to connect it to. right? I update that specific register or that specific output. Questions on that? Now, notice this case statement doesn't have a default, but this case statement does. Why? Why does one have one and one doesn't?
The one without the default case is in an always FF block.
Okay. So why doesn't it have one then? Like, what's special about the always FF block? What's the difference between these two pieces of hardware?
The always comb is well, combinational, and the FF block uses a sequential logic, uses a register.
Yes. And so that is the difference, right? You always need a default if it is combinational logic, right? So many of you in 133 got drilled in to always have a default, always have an else, right? That is true if it's combinational, right? Combinational logic always has to have a default because every input has to be defined, or every input combination has to have a defined output, right? Because if you don't define one, then you've essentially created memory. And if it's combinational and you've tried to create memory, it's going to infer a latch, which is not what you want. If it's sequential logic, you're defining flip-flops. Flip-flops are fine, right? Flip-flops are memory. And so having an undefined option, right? Non-default case, right? That is your save state, right? That is don't change anything. Well, flip-flops don't change, right? That's fine, right? That is what they're designed for. So having that save state fits within a sequential block. Combinational logic has no save state. And so if you define one, it's going to create a latch, which is going to be bad. So always have an else, always have a default for combinational logic. I don't need a default for sequential. Questions on that? Okay. So that's kind of the last piece, or that is the last piece for hardware 7. I would recommend that you don't worry about the wrapper until you have done some very thorough testing in the sim for test all, right? So you could put the wrapper in and you could sim it with the wrapper in there, but you're basically just adding logic that isn't really worthwhile for testing, right? You don't need to test the wrapper. I wrote it, it's good. You can kind of trust it that it's fine. So adding it in there sort of adds an extra complexity to the testing that's probably not worthwhile. So I would, kind of exactly like I did in class, right? I took that CPU component and I ran test all and tested it, right? And so after you have it where you can see it's going through all of the test cases, you're not getting to any 22Cs. You kind of see that it's outputting to LEDs that seem to be working right. It's counting through on the 7 seg. That seems to be working. After you have that, then I would put in the wrapper, add the constraints file, and then spend the CPU cycles to create that bit file and test on hardware, right? But testing on hardware to then see an LED doesn't light up, you then have to find where that is in your assembly code, which is not difficult, but it isn't trivial either. And so, right, then you got to find where it is in the assembly code, and then you got to turn around and find that in the sim, right? And finding that sort of time correlation is iffy to do, right? It's a whole lot easier just looking for problems just in the sim. It's kind of easier to sort of jump around and kind of see what you're looking for if you can find the problem there first, right? So that's why I said debug all of those first and then put it in the hardware, right? Otherwise, you will spend countless time making new bit files over and over and over again. And that's really time consuming because Avado is not known for being fast. So that would be my recommendation, right? Make sure the sim looks good, then put it into a bit file. For hardware 7, right? The verification, the good thing is that I don't need to see any sims. In fact, I don't want to see any sims. I'm going to see way more than I need to see, I'm sure, in the next week. Your verification is you will demo, right? You will show me your basis board and we will see it light up LEDs and count on the 7 seg. And so next Friday when that's due, that's all we'll be doing, right? So there'll be no lecture next Friday. It'll just be 2 hours for you to show me your working hardware 7. And so I'll be here to help those that are trying to wrap it up. How I typically handle it is I always prioritize people that are done. So if you're done and ready to show it to me, you move to the front of the line to make sure that everyone that's done has a chance to demo. And then after everyone that's done, then I'll help whoever isn't done yet. Questions? It's getting exciting.